Okay, 3, 2, 1. Welcome back to another exciting video of the online section of Math 2070. And today we're going to talk vector equations. Today, or this video. Maybe you're watching every single video in one day. I don't know what you're doing. Okay, so let's talk about a special kind of matrix, a matrix consisting of one column. We'll call that a vector. So, for example, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, let's talk a little notation here. So this vector has two entries, and the entries are real numbers. In particular, these are actually integers, but those are real numbers. And so this one we'll call that lives in R2, because there's two of them, and they're real numbers. R3 and R4. So on and so forth. And vectors in general we'll represent using a bold symbol. So bold U would just mean that's a vector. Now, vectors, we have some operations we can perform with them. So let's take our vectors U, which is the vector consisting of 1, 2, 3, and V, which is the vector consisting of 4, 5, 6. I can add them together, and they add together the way you think they should. 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. I can also scale them by a constant, and that works the way you want it to by simply multiplying every entry by -2. And these operations behave how you should expect. So there is a big old fat list in our textbook explaining the basic things that scaling and adding will work with. This one right here is my particular favorite one, which says that if I scale a vector by a sum of two scalars, then it distributes accordingly. Now this one I really like because there's some subtlety going on here. Note this addition. That's the addition of real numbers. This addition, however, is the addition of vectors, so this is like kind of a conversion property. So I always thought that was a really neat little fact here going on with this distributive fact. Now, another interesting fact worth pointing out is that the vector consisting of all zeros behaves as expected, because if I take a vector and add the zero vector, I'm just adding a bunch of zeros, so nothing happens. And as is tradition, there is no such thing as subtraction. There is only addition by negative things. So when I scale by when I write out 2u minus 3v, I really mean 2u plus -3 scaling v. All right. Now, something that we like with vectors is creating linear combinations, and this should hopefully look a little familiar because we've seen, hey, take things, scale them, and add them up, because that was our new equation for a line. So obviously doing this for vectors is something that I'd be interested in doing. And vectors, of course, one-column matrices. We like matrices, so it's all going to coalesce together here in a moment. So, like I said, we like these for many reasons. So, for example, here is a beautiful system of linear equations. Just kidding, it's a linear combination of vectors, because if I rewrite the coefficients of x1 as the vector a, consisting of 0, 4, -1, the coefficients on the variable x2 being woo, man, these are bad. What the hell's going on here? These are totally wrong. What? Excuse you. Let me. Oh man. All right. Well, do it live. All right. So b is x2, and x2 has a 1. Man, what is going on? These are way wrong. I vaguely remember this now. I think from the last time I used these notes, I think somebody emailed me and said these are totally wrong. And of course, me being the consummate professional, I never fixed it. Oh my god. All right, and then the right-hand side's fine, and then C, which is being scaled by x3, there's a 5, a -1, and a 3. And so let's go ahead and fix this. Jesus Christ. There you go. And oh, there was no 3 here. There's a 0 there. What am I doing? That was right. I'm just tripping myself up here. Now you may be asking yourself, you are previously recording this. You could stop and re-record it, And you might be correct, but as my very good friend Alex Andriotti would say, "Now, man, when you mess up, everybody learns." So I like to keep these goof ups in the video because man, then now you've learned that I'm completely and utterly incompetent and should not be trusted. Uh, Okay, and also note that it's pretty easy to trip this stuff up, even though it's might be seemingly simple stuff here. It's pretty easy to goof up things, and yeah. We right, they're not mistakes. They're only mistakes if you repeat them. All right, cool. But anyway, here we go. This beautiful system here, I have now properly converted over to a linear combination using my x1, x2, x3 as my scalars, even though they're the unknowns, and my a, b, and c corresponding to the coefficients on them. So again, there is no x1 up here. There is 4 x1s here, negative 1 x1s there. There is 1 x2, no x2, 3 x2. There is 5 x3, negative 1 x3, no x3 there. And the right-hand side, I got out of here unscathed, so beautiful. So this is really nice because this tells me that there is another way of viewing my systems of linear equations. I can view them as matrices. I can also view them now here as a linear combination of vectors in Rn. Pretty cool. So it's probably worthwhile to get some notation on the collection of all possible linear combinations, because we see that systems can be represented as such things. So, given any collection of vectors, we'll call the span of them the collection of all possible linear combinations. Now, it's worth noting that a pretty easy span to describe is just the span of a single element, because it's just going to be all the scalar multiples. And if I want to make this look nice and pretty using wonderful set builder notation, I'll do it as follows. So some braces, and here we'll write the things I'm talking about, the vector A and all of its scalar multiples, and here C is a real number, and we can write that concisely as C, this cool little symbol, which in the old days of math was actually an epsilon. It's got a little bit more stylized over the years. So this reads as C is an element of the real numbers. Okay. So the span of a single element we're really not going to talk about too much because it's pretty boring. It's just the collection of all scalar multiples. We're only going to be a little more interested in spanning sets that fill up all of Rn. Or Rn, while we could technically talk about R1, R2, R3, and beyond are a little more interesting. Now, it's worth noting that a spanning set always exists, because if I look at the elements E1, E2, up to En, which have 1 in the corresponding location, here 1 in spot 1, 1 in spot 2, 1 in spot N, then if we just think about any vector in Rn, which looks like x1, x2 to xn, well, then I can just pull this apart accordingly. It's just the linear combo of the E1s to the Ens, using the entries as the scalars. So we always have access to these. This is usually referred to as the standard basis elements. We'll talk a little bit more about that later. But let's get a more interesting example. Here are two vectors in R2, 2, -1, and 2, 1. The elements of the span must be anything that looks like a linear combo of these two, so scale them by C1 and C2 and add them up. So now my question is, what things look like this? So in other words, we'll pick a random vector u, call it u1 and u2, and in order to be in the span, that means u1, u2 needs to be this linear combo. And as we just noted, linear combinations of vectors are really systems of linear equations in disguise. Now I can set this up in an augmented matrix as follows, and perform some row operations. And here I'm being very careful because in this situation, our right-hand side, now note if we go back here, our right-hand side were these variables u1 and u2 that we don't know because we just said pick a random vector. This is our first time kind of encountering this, where we have a matrix with variables inside of it, which is totally fine. So I'm going to do the row operations very carefully. So I'll scale the first row by by 1/2 and add it to the second. And I'll scale the second row by -2 and add it to the first, and then I'll do some scalars and give me this. Now this reveals that C1 is negative U2 over 2 plus 1 U1 over 4, and C2 is U2 over 2 plus U1 over 4. Now note, if we plug this in now, this tells me my vector U can always be written as a linear combination of A and B, where the C1 and C2 are based off of U. That shouldn't be too surprising because U, again, was a randomly chosen vector. But this reveals that every element of R2 is a linear combination of A and B, meaning that our vectors A and B are in fact a spanning set of R2. Now, this is some pretty heavy analysis. This was, right, there's a lot of variables, a lot of ins, a lot of outs, a lot of what have yous running around. And while this is all well and good, we are going to get a much better method for solving for all of this, because while we have now seen that linear systems can be converted over into vector equations, we know linear systems are also matrices, so there's got to be some deep connection between those two, and I wonder if there's a thing called matrix multiplication that connects the two together for us, and perhaps we'll see that in the next video.